speaker is Dr. Jeff Diebold, and his presentation is titled Variable View Factor Two-Phase Radiator. Dr. Jeff Diebold obtained his PhD in aerospace engineering from the University of Illinois as a member of the Aircraft Icing and Aerodynamics Research Group and has over 10 years of experience in experimental aerodynamics and fluid dynamics. He joined Advanced Cooling Technologies as a research and development engineer in October of 2019. Since joining ACT, Dr. Diebold has been involved in several SBIR programs to develop novel thermal management concepts with a focus on concepts providing passive thermal control. Welcome, Dr. Diebold.
All right, thanks. Okay, so again, my name is Jeff Diebold. I'm going to be discussing the work done at Advanced Cooling Technologies to develop a variable view factor two-phase radiator. So I want to acknowledge my other co-authors here, Colleen Theroux, Andrew Lutz, and Srujan Rokum, all from Advanced Cooling Technologies. And we also want to acknowledge NASA funding us on an SBIR program and our technical monitor, Jeff Farmer. Okay, so this work was inspired by NASA Technical Roadmap. They're looking for variable geometry radiators capable of high thermal turndown ratios. As part of a phase 1 SBIR, ACT developed a novel variable geometry radiator that was able to achieve a thermal turndown ratio of approximately 37:1. This design was fully passive, scalable, and deployable. Here are just a couple of simple sketches of the concept. When it's at low temperatures or low power, the radiator is closed, and as that temperature increases, the radiator opens up to increase the surface area available for radiation. And then there's also a multi-panel concept, which is deployable. So as the temperature heats up, the radiator expands, increasing the surface area available for radiative heat transfer. So the concept developed by ACT utilizes a curved panel that's formed by using two thin metallic walls, forming an envelope with a hollow space in the middle, which here is labeled as the vapor gap. Within this hollow space is a two-phase saturated fluid. As heat is applied to this system, this two-phase fluid temperature and therefore pressure begins to increase, and this increasing pressure causes the curved panel to open up. We can see that in the images over here on the right. As the system heats up, the curved panel begins to flex, opens up, increasing the surface area of the heat transfer of the radiator, or increasing the view factor. And then as it cools down, the system closes back up, decreasing the view factor and increasing thermal resistance. So here we have a quick video from the phase 1 SBIR prototype. So in the plot here, we can see temperatures of various thermocouples on the surface are rising. And eventually the system starts to open up. The view factor is increasing, allowing for more heat transfer. Then as the system begins to cool down here, we'll see in a second, it will start to close, increasing thermal resistance with the goal of attempting to maintain the vapor temperature within the system and minimize temperature swings of your electronics. And eventually the system will return to its fully closed position there. So the phase 1 concept, which we just saw a video of, shown here on the left, utilized a stainless steel flexible section that you can see here. And this flexible section is one continuous vapor space. In the image, you can see there are some spot welds along the envelope there, which were used to help contain ballooning from the high pressure of the fluid inside. The flat panel portion of the radiator was a separate aluminum sheet connected to the flexible portion that used aluminum heat pipes to help transport the heat out along the flat surface there. So in phase 2, we are working on an updated concept. There are several changes we're making here. First, we're going to construct the entire system from an aluminum alloy, high strength aluminum alloy. Then we're going to have several modular or several strips, which we can see here. In this schematic, there are 4 separate strips. Each of these strips is actually now a continuous vapor space. So from the curved panel all the way through the straight panel, is all hollow, containing the saturated two-phase fluid. So this has a couple of advantages. First, it minimizes thermal resistance between the curved panel and the flat panel. So because it's a saturated two-phase fluid, the entire system should be nearly isothermal. And then by using several modular strips, shown here as opposed to one single vapor space, we can increase reliability of the system. If one of these strips here were to have a leak and lose its fluid, the remaining strips are still capable of operating. And then we can also add ribs, shown here, or potentially just spot welds like we did in phase 1, in order to increase the structure's capacity to contain the pressure. So in this talk, I'm going to be focusing on some 3D structural modeling and some thermal modeling that we've been doing at ACT. So the structural modeling that I'm going to show was done using Abacus. Simulations were performed for individual channels. So a quarter model of a channel is shown right here. So symmetry boundary conditions were applied along this edge as well as the center of this channel. So within this channel, a pressure was applied to all internal surfaces to simulate the effects of the vapor. Some of the relevant variables to look at include the wall thickness of the envelope, the space available for the vapor or this vapor gap, and then the width of the channel. And then for the variables that define the profile, so this teardrop shape here, are the radius of curvature of the bent portion, and then the height, the total height of the radius. There's also the depth, the Z, which is here just the number of channels multiplied by the channel width. And just pointing out here that there's a case where this angle theta, when that's 90 degrees, the profile becomes a circle rather than this teardrop shape, and this represents a very compact form. So in order to quantify the amount of opening, we calculated the view factor, or the amount of radiation that would leave the radiating surface, or the inner surface of the radiator, and travel to the exit plane, or surface 2 here, which would then travel out into space or to your heat sink. So for these calculations, it's assumed that the end caps are closed at all times. This represents a conservative estimate. Closing the end caps off or blocking them is desirable when the system is closed. But as it opens, we would want those end caps to also allow heat to escape. But in these calculations, it's just assumed the end caps are blocked, and this represents a conservative estimate of the view factor. So I won't go through the math that we did here, but the view factor was calculated by taking the deformed profile, which was extracted from the 3D simulations, and then using the deformed shape, the view factor between surface 1 and surface 2 was calculated. So here you can see the effects of the profile and pressure on the opening. So in each plot here, represents a different possible profile. So this top left here is a circular profile with a radius of 6 inches. On the right, this is a circular profile with a radius of 4 inches. And the bottom two are the teardrop shapes, both with a 4-inch radius, but different total heights to the system. Then the lines here, the different lines represent the deformed shape of the radiator extracted from the 3D structural simulations at different pressures. And here it was assumed that the envelope material was aluminum. This just defined the modulus of elasticity. Plastic deformation effects were ignored in the simulations. It was assumed that the pressures are low enough that has not occurred. And the wall thickness was 25 thousandths of an inch, and the channel widths were 2 inches. So we can see here that as the internal pressure increases, the radiator begins to open, significantly increasing the view factor. We can see the rate of the opening with respect to pressure is nonlinear. The larger radius radiator here experienced initially slow increase and then a rapid increase in the opening rate, and then it reduced or decreased again. The 4-inch radius case seems to experience just a gradual increase in the rate at which the panel is opening. So we can look at some quantitative data here. We performed parametric analysis, looking at some of the effects of some of the different geometric variables. So in this plot, we're looking at the effect of the wall thickness of the envelope on the view factor of the radiator. So we have wall thickness on the x-axis here, and then lines representing several different pressures. So as we'd expect, increasing the wall thickness results in a significant increase in the stiffness to the system and a reduced view factor for a given pressure. But as we decrease that wall thickness, we can start to see a rapid rise in the view factor. So in addition, though, however, there are trade-offs. A thicker wall would also help to reduce stresses and contain the pressure within the envelope. It also offers increased protection to micrometeorite damage. So again, if one of the panels leaks, we would lose some of our ability to open the system. You can also look at the effect of the vapor space gap. So increasing this gap here is going to result in a stiffer system. And so we can see that here in these plots, which are again view factor versus the vapor space gap for several different pressures. At lower pressures, the vapor space gap doesn't have that significant of an impact. But once we saw earlier, as the pressure increases, the rate of opening begins to increase. And so once we reach higher pressures, we see a larger effect of that vapor space gap. So increasing the gap is going to reduce the opening by increasing the stiffness of the system. It will have an advantage in that it will reduce the pressure drop of the vapor flowing through the system. And then I also looked at the effects of the channel width. So here, view factor versus channel width for several different pressures. And we can see the channel width has a significant impact. Increasing the channel width results in a large increase in the view factor, and that effect becomes more pronounced at higher pressures again. So again, we've got improved opening for larger channel widths. However, this will lead to higher stresses and potential ballooning, which may need to be contained using spot welds. And then we also have fewer channels for a given depth of the radiator. And so this might reduce reliability of the system. The fewer panels or the fewer strips that we have, the larger penalty we might pay if one of the strips were to leak. Here we can see the effects of the profile and pressure on view factor. So in each plot, we see view factor versus pressure. Each plot represents one of the four profiles that we've been looking at. And then within each plot, the separate lines represent different depths of the radiator. And so again, the depth here is just the number of channels multiplied by the channel width. So as we increase the number of channels, we see an increase in the view factor because of a reduced effect of the end caps, which again were assumed to be blocked. So we can see for the different profiles, there can be a difference in the rate of the increasing view factor. So again, the 6-inch radius case here sees a rapid rise in view factor at lower pressures than the profiles with 4-inch radius. However, the 6-inch radius profile does begin to, the rate of opening does begin to decrease here. And so we see for all four profiles, the maximum obtainable view factor within the pressure range that was simulated here. We're all pretty similar, maxing out at around 0.7 or so, with some small differences. Another useful way of looking at this, rather than simply the view factor, is the effective area, or the product of view factor and area. So if we're looking at our equation for radiative heat transfer, this product here is a measure of the thermal conductance of the system. So now when comparing these values for the different profiles, we can see significant differences. So for example, comparing the 6-inch radius profile to the 4-inch radius, we see even though they had comparable view factors, because the actual physical surface area of the 6-inch radius profile is larger, we have a much higher effective surface area available for heat transfer, and therefore lower thermal resistance if all other variables are kept equal. Similarly, looking at the different teardrop shapes, we can see that increasing the height of the panel will also result in a significant increase in the effective thermal or the effective area available for heat transfer. So using the simulation results, we performed some preliminary thermal modeling. So we wanted to see how the temperature of the system changed as the environmental conditions were changed. So some assumptions here, it's assumed that the entire internal surface is isothermal, which is a reasonable assumption because we have, again, a saturated two-phase fluid within those channels, which should be at a constant temperature. And then in this model, we're assuming right now that the outer surface is perfectly insulated. So in this model, we have radiative heat transfer from the inner surface, and then thermal resistance from the vapor to the sink. So this accounts for, there's a term for condensation on the inner wall of the radiator, conduction through the envelope, and then resistance from radiative heat transfer. In these terms, or in these equations, the view factor term here was determined from the simulation data. So the simulation data provided view factor as a function of pressure, but because in a saturated flow or a saturated fluid, the vapor pressure is related to the temperature, we can relate the view factor to the vapor temperature. So in order to perform these calculations, we had to make some choices for some values. So it's assumed that we are dissipating 40 watts, a maximum allowable vapor temperature of 60 degrees C, and a sink temperature ranging from minus 130 to positive 20 degrees Celsius. The required effective area to dissipate Qmax, or maximum power, into the maximum sink temperature is 234 inches squared. So you can use this information and the simulation data to determine the appropriate depth of the different profiles necessary to dissipate this load. So for example, well, first, it was assumed that pentane was the working fluid. This pentane was selected only because at the maximum selected vapor temperature, pentane's vapor pressure was within the range of the simulated data. So this isn't to suggest that pentane is necessarily the best choice. It just fit within the simulated data that we already acquired. So the plots here show that for the 4-inch radius circular profile, in order to dissipate 40 watts at the maximum temperature into the maximum sink temperature, you would require a depth of approximately 24 inches to acquire the necessary effective area to dissipate the heat. So we can then size the radiator using these plots. By going to the teardrop shape and extending the height of the radiator, we can obtain the necessary effective area at a shorter depth of only 14 inches as opposed to 24. And similarly, we can determine the necessary depth for the other two profiles as well. The plot here on the top left now shows the variation in vapor temperature within the variable view factor radiator as a function of sink temperature for those 4 separate profiles. On this plot, this case here, the black dashed line is a standard radiator. So this is a simple flat plate radiator with a view factor of 1, but this view factor is fixed. There is no changing geometry. And we assumed a radiative efficiency of 0.85. And this flat panel was sized to dissipate the 40 watts at the maximum vapor temperature and maximum sink temperature. So we can see the flat panel radiator, which is unable to vary its thermal resistance, sees a large temperature swing in the vapor of approximately 60 C as the sink temperature varied from positive 20 to negative 130. The 4 different variable view factor radiators, however, saw much smaller temperature swings of approximately 10 to 15 degrees. On the right here, we can see this was a plot of the view factor versus pressure for the different profiles. So looking down here, we've listed the actual physical surface area required by these different radiators. So we can see, for example, that the case where of the 6-inch radius profile had the smallest physical surface area of all of the variable view factor radiators. And this was because at the maximum pressure, that particular profile had the highest view factor. And therefore, it could have a smaller physical surface area in order to obtain the necessary effective surface area. We can also see that there is an effect here of the slope of view factor versus pressure. For the case of the 6-inch radius profile, because the slope of view factor versus pressure is rather low compared to the other radiators, That system required a slightly larger drop in temperature in order to decrease the view factor. And we see that illustrated here, where the 6-inch radius profile had the largest temperature drop of the variable view factor cases, although it's still quite small compared to the standard radiators. So we can see that the variable view factor radiator is capable of maintaining a relatively constant temperature despite a very large change in the sink temperature. Now, because the maximum view factor of these variable view factor radiators is less than 1, they do require a larger overall surface area compared to the flat panel radiator. Despite this fact, one of the advantages of the variable view factor radiator, as we just saw, was maintaining a narrow range of operating temperatures, but it will also allow for a reduction in heater power requirements during survival mode. So as an example, if we assume that for the case above, if our electronic survival temperature happened to be negative 30 C, and we represent the electronic temperature by vapor temperature. So at a survival temperature of minus 30 C and a minimum sink temperature of negative 130 C, the standard radiator, the flat panel radiator, would require approximately 25 watts of heater power in order to maintain the vapor at or above minus 30. The variable view factor radiator, however, would only require approximately 1/3 of a watt of heater power. That's due to the significant increase in the thermal resistance. At negative 30 C, the view factor of this particular radiator is approximately 0.005. And this could be even reduced further all the way down to 0 by simply extending the length of the panel slightly so that it's fully closed at your survival temperature. All right, so in conclusion, we have successfully at ACT demonstrated a prototype of our novel variable view factor 2-phase radiator. The system's fully passive and capable of achieving a high thermal turndown ratio. The advantages of this concept are that we obtain an isothermal surface due to the 2-phase fluid inside the envelope. This gives us a high thermal or a high radiator efficiency. We minimize the effect of the environment on the operating temperature of the electronics, and we can see a significant reduction in heater power requirements during survival mode. And then also the system is automatically deployable. In the fully closed position for launch, it can have a smaller footprint than the equivalent flat panel radiator. So currently we're working to further optimize the envelope design. And we are also working to optimize the manufacturing process. And we're currently working on using ultrasonic welding, which will be compatible with the high strength aluminum alloys that are ideal for this application. And then this will be followed by prototype testing. So with that, I'm happy to take any questions.
Yes, thank you, Dr. Diebold, and my apologies for butchering your name on the introduction. So we've got 6 or 7 minutes for questions. Bill, do we have any come in?
I'm looking at the chat right now. Let's see. Yeah, we have a couple. The phase 1 test looked like it was fighting gravity in opening and closing. How would microgravity operation affect performance, particularly the transition temperatures?
Yeah, so we're sure that gravity was playing a role in how much it opened in phase 1. So in all of the simulations, right, there is no, gravity's not included. So we would expect that we wouldn't get the benefit of gravity helping to open the system, and we'd have to rely entirely on the internal pressure. And so that's how the system is being designed. But also I want to point out, if we go back and look at the picture of the video here, this prototype, gravity is going to be playing a stronger role than it would in the kind of updated concept I've been talking about, because again, this flat panel here with these heat pipes attached is going to be significantly heavier than the equivalent flat panel portion of the new radiator, which is just made up of 2 sheets of very thin aluminum that have been welded along the edge. So gravity would play a smaller role in the updated concept than it did initially as well. but we're designing the system assuming that gravity is not helping to open.
Okay, we've got another question. How long did it take to transition from open to close and back during testing?
Well, if we look, well, it's going to be just a function of how rapidly you're applying heat to the system. So, I mean, this system here was just simply an ambient. There's a heat pipe here connected. I'm not sure exactly what the power was here. But you can see down here on the x-axis of this plot is time. So you can see this video is sped up. This is happening over tens of minutes. But again, if heat were applied faster, the system would be capable of opening faster.
Okay, thank you. I don't have any more questions. I guess we'll give it another minute or so here to account for the delay. All right, we've got another question. Would some optical coatings not be compatible with this technology due to the flexing of the surfaces?
Yeah, that's possible. We haven't started to look into that yet, but we will have to consider the fact that the deformation of the structure may interfere with any kind of coating we apply to it.